I will be talking about DESY and its implications for dark energy theories, and some of the slides may be repetitive from the earlier talks. So this is the first DESY result which talks about the posteriors in the omega A and omega naught plane, and I will talk about that why this omega A and omega naught plane is important to define the dynamics of the dark energy. So when we combine only two observations, for example, only DESY and DESY and supernova. So for the case of DESY and the DESY Pantheon plus, the lambda CDM point is between 1 and 2 sigma. But when we consider the union 3 and DESY 5 observation, this is beyond 2 sigma. But when we combine all these three observations, DESY, CMB and supernova, the discrepancy goes away from the 2 sigma regime. So for example, in the case of Pantheon plus, it is around 2.8 or something, and in the case of Union 3 and DESY 5, it's beyond 3 sigma regime. So this is one such result, and this result can be systematically oriented or maybe theoretical inaccuracies. So when we talk about the systematics in the Pantheon plus observation, and we have this intrinsic parameter of this Pantheon plus, which is the absolute magnitude. So when we consider two anchors, for example, the early universe Planck and the late universe Schurz, so we see that there is a discrepancy of more than 2 sigma in the absolute magnitude parameter. So this is a systematic error in the Pantheon plus measurement. Also, when we consider the GRB data, again, if we consider two anchors, for example, the Planck and the Schurz anchor, so again we see that there is a discrepancy of more than 2 sigma in the intrinsic parameters of the GRB observation. So this is about the systematics. Again, if we bin the Pantheon sample in different redshift bins, so if we set some minimum redshift or if we set some maximum redshift in the sample of Pantheon plus, which is 1701. So when we consider the minimum redshift to be around from 0.0 to 0. Let's say 15, then we see that they are consistent with omega m value. But when we go beyond that cutoff, we see that the omega m is running, and a similar thing we see if we set a maximum redshift. So this could be attributed to the number of samples we have in the higher redshift regime. For example, if we go, so if in 1701 samples of Pantheon plus, if we go beyond let's say 0.5 or 0.7 redshift, the number of sample is quite small, which is around 100, and most of the samples are below these values. So maybe that is the reason we see this running of this omega m. So in the paper, Malikjani et al., they thought about this idea, and they were using this actual data of Pantheon plus. They considered some different polynomials of this function, luminosity distance, and they fitted this model with different polynomial curves. So what they found that the most fitting curve is this function, the cubic power of redshift, and using this polynomial, they extended the number of samples for a higher redshift regime, and they created some mock data using this curve and this error bars of these observational data. So what they have found that if we equally divide the number of samples for less than 1 redshift and greater than 1 redshift, so again we see that there is a discrepancy between these two redshift, and they considered up to 10,000 samples of supernova. Maybe if they consider more samples, then they can, because we see that this is the behavior is going down, so maybe there is a consistency if we go beyond that 10,000 number of samples. So this is about the systematics, and similar thing we see in the RSD measurements of this S8 parameter. Again, we consider some redshift bins, we see the running in this S8 parameter. So again, as Sharik was talking about this negative neutrino masses, so in the new RAC paper, when from CMB alone, if they set priors on this, some of the neutrinos masses are free. So we see that the peaks are not in the positive but in the negative neutrino masses. And if we combine all those DR2 and CMB baseline observation, so the error bars have reduced, but again the peak is around minus 0.11. So again, if we plot this volumetric distance with lambda CDM, and we try to fit this graph with different sum of neutrino masses, so we see that the most justified line is with this negative neutrino masses. So, and this is considering the background lambda CDM model. So, as Sharik was shown some interesting result that if we consider some dynamical dark energy, we can shift these peak to the right side, and that would be a very interesting result. Again, further, if we free this parameter, so there is a direct correlation of this sum of the neutrino masses with the H naught. So again, in context of Hubble tension, if we want to increase the value of Hubble, then we have to consider this negative neutrino masses in lambda CDM regime. And again, if we put this negative neutrino masses around this value, it perfectly fits this DESI band. So this is the neutrino problem that we have with lambda CDM model. And so these are the problems in the lambda CDM. So that's why we need to look beyond the lambda CDM. And again, in the DESI paper, Lodha et al. Paper, they reconstructed different cosmological parameters using these Biot data, and they found that this is equation of state. This is not a constant, but it has a dynamical nature with different combination of data sets. And this is the energy density fraction, again, which is not a constant, but it is it has some dynamical behavior. And this feature I want to focus on this feature because in most of the recent works we have found these features in the dynamical dark energy models. And this is the residual with compared to the lambda CDM model, and we see that for high redshift the lambda CDM and all those DESI dynamical dark energy thing, they are almost similar. So all those dynamical thing is affected in this 0 to around 1.5 redshift regime. So that's how we need to look beyond the dynamical dark energy models. And how can we do that? So when we interpret those data, so we have to have in dynamical dark energy models, we have to have the dark energy must evolve, super evolve faster than the Hubble friction after the matter domination. And dark energy should cross this -1 line, which is the phantom divide. And recently, it has deviated away from lambda CDM. So how can we do that? So these are the two classes of dark energy that we have. One is the thawing one and the freezing one, and these are different regions. So in these regions, some of the standard principle have to be violated to lie the dark energy in these regions. And these are some dynamical. These are some dark energy models that comes under these thawing and freezing scenarios. So we have these four regions. One is this high region, middle region, low region, and there is phantom region. And the observation suggests that the dark energy is lying in this high region. So we can go from this W prime to W region to W naught WA plane. When we consider W prime to be minus WA, so when we take the Taylor expansion in first order, and then we put W prime to be W minus WA, and then we have this W naught as the the first the ground value. So we see that in the most in the Desi paper we are getting this regime below this regime, and what are and we see that this WA and W naught plane justifies the dynamical behavior of the dark energy. So instead of taking the Taylor expansion of the equation of state, because most of the cosmological parameters are related with equation of state indirectly, they have first order integral or second order integral with the equation of state. We can directly expand the dark energy around the cosmological constant, and we can take the Taylor expansion of this dark energy, and it can have, depending on the model parameters, it can have different features. So we use this expansion, and then we get a very compelling evidence for this dynamical dark energy, and we see that for 3 extra degrees of freedom, we have this is around 99% confidence level, and this is beyond 99% confidence level. We are getting the evidence of this dynamical dark energy, and when we reconstruct the energy density, we see that this is the feature that we are getting, which we see in the Desi paper. And lastly, this is the Hubble plot that we see, and we see that the Desi Biot data point and the SDSS Biot data point are justified by this model. So with this, I will conclude my talk that the impact of dark energy on observation is superbly accounted for in the W naught WA plane, and then we have certain zones of avoidance, and instead of taking the W Taylor expansion, we can take the dark energy expansion directly, and in the upcoming observations we will have those tight constraints on these cosmological parameters, and in the stage 4 stage 5 Desi observations, we will have 10 to the power 8 number of observation, and then we can get a more tighter constraint, and then we can talk about these different dark energy models.